And we are live, apparently, supposedly. Welcome to MySec Detroit. Woo! MySec Detroit. This week we are talking about linters and the ones that are not just for belly buttons. And we're going to start off MySec with what I think is a tradition, the typical flow of things. Announcements. For one, I want to thank everybody for coming out. This is the first one of many. So hopefully to see some more faces, including some of the same faces that we see here today. I don't have any other pressing announcements. I want to thank our speaker, Picat, for coming. I want to thank our gracious host, Collider Detroit. Actually, I want to give Collider Detroit a moment to speak. Jacob, on behalf of Collider Detroit.
I'm going to try to address everybody and talk into the microphone. I just wanted to say welcome, everybody, for those who, I think it's a lot of people's first time here. Space is called Collider. It's sponsored by a company called Ultimetric. It's actually a global software services firm headquartered in Southfield, Michigan, that does like digital transformation work. So it helps large corporate clients stay ahead of the curve with technology change. Working on a lot of, in Detroit specifically, working on a lot of mobility tech, kind of cutting edge autonomous vehicles and some different things, really cool stuff. What we're doing here is we are doing, as you see tonight, lots of different events focused on building community amongst technical professionals, amongst software professionals. So we are hosting multiple events per week. You can see it flashing by on the screens and everything, ranging from presentations to workshops. We're going to be ramping up with coding tournaments and a bunch of different exciting stuff. So I encourage you, these flyers that are on the tables, that has our social media info and meetup. I encourage you to check it out, and or just ask me if you have any questions. And then the last shameless plug is just that we are actively hiring. So if anybody is looking for a job or knows someone that's looking for a job in software, specifically Java engineers, mobile engineers, and data scientists, please come chat with me. Other than that, please, we'll see you soon.
Make sure. All right, cool. All right, cool. And do we have? I want to open the floor. Does anybody else have anything that they want to announce? Any job openings? Any speaking opportunities? Any? No? All right. And with that being said, I'm going to let Picat get after it.
Cool. Thank you guys so much for coming. So yeah, linters, not just for belly buttons. Oh. Cool. All right, so hi, my name is Kent Gruber. I'm a product security engineer at HashiCorp. I was hired a few months ago. I've been working there about 6 months. I really enjoy working remote. We're hiring, so I recommend you check out what we have to offer. And basically today, the main focus is on static analysis. So this is effectively a method of the software analysis of just looking at basically the raw source code effectively and trying to figure out basic security information is what we're going to try to grep for today. And basically, it's this very simple pattern where basically we have basically the actual software that we load, and then we have like basic rules that we apply to that software, and then we collect that somewhere. So like on disk, maybe in some sort of like cool cluster Elasticsearch somewhere, wherever you like really. And really why? The main like kind of goal is to be able to share knowledge as code. So if I have a security like domain specific knowledge about maybe some part of a language, it's very helpful to be able to share that security knowledge by having a tool that you can run against your code base, and that allows me to share my knowledge as code, right? It also like kind of like helps like just in general, like help automate, finding bugs at scale. If you can find a class of vulnerabilities with static analysis, you can have a tool that can do that generally. You can run that against like all, the popular code bases in X language that you're looking at. And so there's a bunch of flavors of source code that we could be looking at for static analysis. So effectively, I kind of broke it up into two, but effectively there could be more, however you want to look at it. But basically application and infrastructure kind of code, you could look at it. Because infrastructure as code is very popular. Working in HashiCorp, Terraform sort of thing, very popular. Try to do a kind of everything as code. And those like kind of things, whether it's like AWS IAM policies, a lot of things are these effectively these data structure languages, YAML, JSON, HCL. And then you have like the application application side of those things, which maybe those things are spinning up the infrastructure, and then the actual like stuff is maybe running using Go or Java, etc. So, kind of neat things we can look at, just like static analysis for like the data structure languages, like for Terraform. Like we could look here that you're actually like storing the password in plain text, so the username and password are just there. And depending on like what your security model is, if you have multiple developers working on the single Terraform code base, we don't have to store them in plain text like this. We could use other tools, such as like HashiCorp Vault, in order to actually manage those credentials securely and be able to have short time to live credentials. We can just grok like that we're doing an insecure coding practice, obviously just by looking at the infrastructure code. AWS IAM policies, a very similar thing where we're looking at like what things you're able to do in your AWS environment, right? In this case, this is like doing something you probably don't want, depending on like what this application is doing and what it's set up to do. It's confidential, be able to get and list anything inside of that bucket. Changing password, like maybe we should break up this policy or do something along those lines. Of course, like even like the general like applications that are running on your box, like sudoers, right? It has a sudoers file, and that's actually a specific like kind of like custom language that's famously described in eBPNF format. If you look at the man page for sudoers, it's actually quite hilarious how like unreadable that thing is. But we're gonna kind of get into like what eBNF is if you don't know what that is, just in a few more minutes here. So the main thing we're going to be really looking at today is an application language, Go. Go's become very, very popular over the last couple of years, and it's a really good language to look at, specifically because there's not too many static analysis tools generally for it, especially for security, though we're going to look at one of them, and then we're going to actually build our own. And I released that, open source that actually today. So yeah, if we look at the code over here on the right, we have, let me just make it bigger on my end here. So we have basically just the package main. We import a bunch of other packages. So Go has the concept of packages, similar to Python modules or Ruby gems, right? Just like other code that we can use that's in some other code base. So these are just like standard library packages in Go. And then we generate some source of entropy with that ran new thing, and then we generate a new multi-prime private public key pair with RSA. This, looks fine, and then we have a message that we want to encrypt using the key that we generated, and then we print that out to the screen. In general, what we would see if we started to run this code, we maybe start seeing just some random bytes. When we're dealing with the data, in this case, these are bytes, and we print that out. We see these numbers, so each number being a specific byte in the bytes slice. So I run that, and it's like, oh, it kind of looks like it's doing the right thing. All the bytes are seem to be random, deterministic. It's only 3 samples, but let's go for it. And I'm very, very curious. Am I doing this securely? So I can go pull an off-the-shelf sort of static analysis tool called GoSec. And GoSec, I just install this with GoGet, and then I run it on that main Go file that has the RSA encryption code that we looked at just previously. But if I do run it, kind of interestingly, it'll say, that's not a directory. And so I look at the man page, or the README for GoSec, and then I see I have to pass in a directory. So I pass in the current working directory with a dot, and I'll see that there's 1 files, which I knew that, and then there's 25 lines, and there's no security or issues or anything like that. So, that seems reasonable, Seems I did my job, I'm a security engineer, did my static analysis tools, heck yeah, right? Okay. So my static analysis tools didn't find anything. Me just looking at it, I didn't have anything. So what I'd have to do in order to be able to find any problems with this is I'm probably going to have to go read a little bit of documentation. Because what I really want is that I really want this kind of clippy character to be able to tell me hey, this is actually an insecure source of randomness. You should be using crypto-rand instead of math-rand. That would be fantastic if the clippy could just tell me this. If clippy could just go read the documentation for me. It'd be really, really great if you could tell me that that source of entropy that I created, that's an insecure source of entropy because of the math rand thing. You're not using the proper thing for cryptography. And then the insecure number of primes. So for the multi-prime RSA key, generally you're not using a multi-prime RSA key when you generate it, though you can. And if you do that, you actually have to pass in the correct max number of primes for this function. Otherwise, you are potentially doing that insecurely, and you can go read a whole bunch of crypto papers on why that's the case. And in fact, I looked at one of them that the Go documentation points to that tells you that this is the table that you should use, and depending on the number of bits that you use, this is the correct number, the correct max number of primes that you should use for this function. And this is pretty straightforward, so it would be really great for it to tell me that this. I'm actually not only just using insecure max number of primes, I'm using an insecure number of bits here. So I shouldn't be using 1024 for my RSA keys. It's not modern crypto worthy. So basically, how do I write a tool to find this? How do I look for that? Right? It's code, it's text, and some code base somewhere. So obviously just grep. Totally, right? We just cat the file, we grep for the thing that we're looking for, the generate multi-prime key, and then we can do some awk magic while we're at it, right? So we can just grep for the things that we want and then start doing some awk magic, and then finally one extra awk magic in order to do a greater than or equal to sort of thing. And that sort of works, but I want you to forget about that for a second. Forget about that dirty way to look for the vulnerabilities in the source code. And we're going to try to do something a little bit more correct, more computer science-y. And we're going to use abstract syntax trees. We're going to actually do real parsing of it. Well, we're not going to do it. We're going to use the standard tooling that Go gives you in order to do these things. It saves me a lot of time. So an abstract syntax tree is effectively a representation of the source code inside of a tree format, and each part of the tree is a node. And these nodes have different types depending on what's going on. So we'll dive into that with just this 3 plus 2 expression, right? 3 plus 2, very, very simple, it equals 5. But we're not storing it as a variable or anything. We're just doing 3 plus 2. We want to look at how that looks like with this AST stuff. So we have what is actually an expression, a binary expression, the plus. And then that is we're looking for, we have the basic literals 3 and 2. They have values that are they're basically the exact same type, just different values. And then we have an operator. And basically this is a very simple way to look at it. And the problems you're usually going to looking for, it's not these binary expressions with pluses or anything like that, but it's a very, very simple way, a very simple kind of AST to look at effectively. And this entire specification of Go, this entire AST effectively is described in eBPNF format inside of the Go documentation. And so eBNF is effectively this family of meta-syntax for formally describing a language. And this is done for some languages, not all languages do this. Go does this. Sudo or file does this. So we're cool with that. Let's dig into this a little more. How do we do actually building a tool, right? This is cool, Kent. I like that there's AST, but how do I have a tool that actually takes advantage of that? So in this case, we're going to, again, use other tools. So we have the Go AST package, which provides that AST file type. We have a Go token package, which gives me this token new file set function. And we have a parser package, which gives me basically the ability to parse a Go file, which is very nice that it has those things available to me. And then I have the AST package has another function called inspect, and I can basically just pass the file, which is sort of the top level node in that tree, right? And then I just walk through that tree. Well, inspect walks through that tree for you, and then calls this other function where we have the argument is a node, and then we check is it a binary expression? If not, well then we're just going to go to the next node by returning true. Do we now check the operator? Is it a token add? Because we're looking for that 3 plus 2, right? If not, well then we're going to go to the next node, and then we're going to just try to go through it until we eventually find it, right? So if we look at the expression and we look at this code as we walk through it, we can see that it's just checking the structure to make it look for something that we actually want. So we can do that not just for the 3 plus 2, but actually for more security related things, such as the RSA package. Any of these function calls, we want to make sure that we're doing it securely. Built a tool to do that. And the reason, well, it's not, so the 3 plus 2 expression, it's very simple, but there's a lot of stuff in the Go AST package, which this is the documentation for, and that's not even all of the functions. Well, Go is a very simple language. The AST analysis part of it is relatively complex, and in general, my understanding is that there's actually very few people building tools for this. which also makes it a really cool like green field to go find bugs in. But regardless, like what do I do about this? Like this is cool. Like there's this GoAST package, this token package, this parser package, but I have all these Legos, like effectively maybe even too many Legos that I don't want to put them all together because it's going to take maybe too much time. I have to read too much documentation. How do I make this easy, effectively, for people to build tools, right? And so the Go team knows that was a really hard pain point for developers that were building these tools. And so they built out this entire framework called Go Analysis, which kind of like what it does is this analysis for Go, right? And basically, it allows you to build out these checkers. And so, for example, we would have a printf checker that reports format printf problems. Format printf being a function from the format package in Go. And there's a whole bunch of documentation that you can read in the Go doc for that at that link. And the real reason why they did this is so that all of the linters that I build up, is I build up not just like my RSA checker, I have that like, fake printf checker, and I build out like more checkers in the future. All of those take quite a bit of time to run through, especially depending on the size of your code base. So we don't want to have basically, let's say 1,000 checkers, and now we have to spawn 1,000 processes and wait for them to finish, but like literally reading the Go code, like doing the parsing, doing the thing, doing the binary expression, walking through the tree, doing the stuff, do blah, blah, blah. And that can take a long time. So the Go Analysis package basically allows you to have a simple framework to hook into that makes it much more efficient. So when you're doing these large code bases, it allows you to scale your checkers much more efficiently on top of actually in general doing less programming, because the framework allows you to hook into a very specific API that's very, very small. I have the ability effectively not only have something that's very fast, but very efficient in terms of the amount of code that I'm writing, which is actually great too. And so like the go vet command, if you're familiar with Go, the go vet tool is sort of like literally a built-in internal tool in Go. And so this is like literally the code for it, minus a few packages, but like that's like, it's a very simple pattern here. We import the package and then we include it inside of this unit checker. So basically we just make a bunch of checkers, then we can add it to our collection, our own Go vet, or even depending on the checker that you write, you could actually get it integrated into the Go standard library as well, because it is just using the checker API under the hood. So we have to build a checker. We know that Go wants us to build a checker style tool. So this is what we're going to do. We're going to create what the checker needs to implement, which is an analyzer. Kind of weird that why isn't it just called analyzer? It has to implement analyzer. It's a checker and it implements an analyzer. You just have to get through that. It's okay. So the analyzer implements an analysis analyzer type, which is just basically the struct here that has these fields, so a name. So we're building that RSA lint tool, remember. So it's called RSA lint, and then it reports insecure usage of the crypto RSA package, and then this run function. So this is the thing that's actually going to run when this linter is called, and we're going to look at that function in a second, but this is just a little internal function that I'm calling here. And then I'm using this other analyzer called inspector, and inspector allows me to have basically like a pre-walked through tree. It allows me to filter the types of nodes that I'm looking at in that tree, so I can have a more efficient way, again, of filtering out the nodes that I want. If I'm just looking for a binary expression, I should only be able to grab the binary expression top level nodes. If I'm only looking for a call expression, I should only grab the top call level nodes. So I can require these other analyzers here, in this case just the inspector analyzer. So this was the code that I showed in the very beginning when we were talking about we were doing Go. We know that it has insecure things because we did a little bit of documentation reading, and we have this like mental clipping now. But we want to share this knowledge. We want to scale it as code. And we want to be able to not just look at maybe this one little like piece of code, but a whole bunch of other RSA stuff in the future. We integrate into our CI/CD pipeline, etc. So just so we understand what we have to look for in the AST, we're just going to zoom in on this one little function here, the generate multi-prime key. So it has the source of entropy, the randomness thing, the R, the number of primes, 9 in this case, and then 1024. We know those are insecure values because, again, mathrand, that table is wrong, and then the insecure number of bits. So so that's insecure there because, I have the prime table there again, cool. And this is the actual table we build out. So we take from that PDF, that table, and basically we just put it inside of this little map, and then we can do a very simple like one-to-one comparison. Actually, in the newest version of the code, these are ints. I changed them from strings to ints, but that's okay. So what this RSA.generate prime key thing, this thing that we're going to try to look for in the AST, it's a call expression because it's effectively doing a function call, and that's what the Golang source has decided to call it call expression. So it's a call expression, and under the call expression, sort of, you can think about it, is that there's an AST selector expression. The selector expression being the RSA, the package, dot. So the dot is basically the notation. This is going to be a selector, and then the generate multi-prime key is the selector. So this would be, in the actual AST package, it would be RSA is X, and then the generate multi-prime key is cell. So what we do is, in our run function, we have this inspect type that we can grab using the inspector analyzer. Because it's there for us, it did that already. I just have to grab it. And the way I do that is just using this result of thing. Using this analysis pass type that's passed into the run function. This allows me to pass in a shared context. This is what the framework does under the hood for you, and I can use that type to do type checking, a whole bunch of different checking. It basically is a shared context value. You can think about it like that. And then, again, I have this filter expression that my inspector wants, and that filter expression is just literally a listing of AST nodes. In this case, they're AST call expressions. Because again, that's what the RSA.generate multi-prime key is. It's a call expression. So I might as well look for those. Then, just to make this slightly human readable, because this code does get a little wily after a little while, I'm going to create these internal helper functions. So I have check secure entropy source, and I have check secure number of bits, and they take in these AST expressions, which could be a call expression, could be a selector expression. It's just kind of like a more generic type for those expression kind of families. And then I can then do the check to basically see if it's using the proper number of bits or the secure entropy source. Then I use that inspect, and I use the preorder function, in this case, just to walk that tree. I then check for each node that it's a call expression, and then if it is a call expression, I verify that it is indeed a selector expression. Because the call expression may not be a selector expression, maybe other types, right? So we might have other function calls inside of the source code. So we're just trying to limit the stuff that we're having in the filter. You could almost kind of, if you've ever done packet analysis before, you can almost kind of imagine these Wireshark filters or Berkeley packet filter sort of things. But in this case, for the source code outside of just packets. And then for each selector expression that I find, I literally just run the checks for the selector type. So that X in cell, I do a little sprintf to make it a string, to do a string comparison, to basically just check that to generate a multi-prime key. And then, again, do the checking with the expression arguments, the function call arguments. So that's the checker code. That was literally the checker code. And then if I want to implement that inside of that API, all I have to do is just create, this is going to be a full command line tool, but this is all the code that I need to write. Because the actual framework did all the hard work effectively for me to create that API. So now all I have to do is just literally register, in this case, a single checker instead of many checkers. And then I just use the RSA check analyzer type that we created. And then now that tool, which has a bunch of other checks inside of it for the RSA package, just because I didn't want to go super too long into all the functions that I wrote checkers for. But effectively, it's called RSA-lint, and it's a Golang linter for the crypto RSA package. That's how you install it. And it's also the link to it on GitHub. And then, so here's an example usage. So you'd install it, and then kind of nice, I can just run it on just the source code file or a directory, or in fact, any pattern that your Go system isn't set up to import. So this could be, it does all the module stuff for you, etc. It's really, really nice in that case in terms of making it a very simple, intuitive API. And so that 12 and 47 and 12 and 53 and all that stuff, that is so your editor, VS Code, etc., knows where to put the cursor. So if I were to click on this, or if I were to integrate this inside of one of those IDEs, it's already set up so that it knows where to put the arrow and put the box and stuff like that, where to direct Clippy effectively. And so that's really helpful, and that's already done. Again, that's just done for me using the Go analysis package if I'm going to use the report function. So RSA-lint can identify a number of security issues in roughly 200 lines of code. And again, it's open source on GitHub. Check it out, contribute, tell me I did something wrong if you're interested in that. basically, you can check for insecure use of entropy, which we know using mathrand is bad. Checking for those insecure hash functions. So we're just saying we want to use SHA-256 and SHA-512 for everything. And then we're generating insecure key pairs, whether you're using the multi-prime or the single prime key. Or let's say you're using the sign PKCS1 V5, whatever that is, right? If you don't know RSA implementation, this is kind of the most famous, the beginning, the sort of the initial one. It's the oldest, effectively, that most languages implement. But that's insecure comparatively to the sign PSS for the signature or the OAAP, which are effectively the same thing, just kind of different names. Crypto's really weird. If you have never dived into crypto, it's really, really weird. But that's what you're supposed to do, at least according to documentation. I'm not a crypto expert, but I can read documentation and I can translate that into some code. And then I can also check for those insecure multi-prime key bits of various sizes, insecure, blah, 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 etc. And just in case you were really thinking that was cool, it gets a little cooler. And so some more cowbell, and I'm not going to dive into too much more else. I'm just sort of leaving, maybe it's kind of at the end here. That AST representation isn't the only kind of representation that you could maybe do analysis on. So if you ever done sort of binary analysis, let's say with a Binary Ninja, for example. Binary Ninja has a static analysis tool for binaries, right? It has a bunch of different architectures that it supports. And what you can do under the hood is it can give you these two levels of intermediary languages. So instead of looking at the disassembly, you could look at a slightly higher level version of the disassembly and even a slightly higher level version of that disassembly. And what's really cool is that's not the only tool that does it. This is a very, very common technique. So for example, Radar2 is another tool that does this, and you can actually output the Python representation or a C representation of this arbitrary binary code, which is relatively cool and especially much nicer to look at as a human to do static analysis of a binary. But we have the source code, so we're going to try to get another intermediary representation, but for our Golang thing, and we're not the only people who have thought about doing this. But just before I share who shared the implementation of that intermediary thing in Go, there's this SSA thing. So SSA is a property of an intermediary language, single static assignment, and it basically allows you to more intuitively walk through nested function calls and assignments of a program. And it doesn't make too much sense when it's described like this, to be totally clear. But if I were to write a little bit of Go code and I were to use these other Go SSA and Go SSA util packages, and I also have this packages package, very meta, I could load up some packages and then I could dump an intermediary representation of that code that isn't the AST code, but is this SSA form of the code. And so if I were to look at the 3+2 expression and I were to dump the intermediary language representation of that, I would see what's in the bigger box where I have this init thing. So in Go, there's this special init function which allows you to do stuff on startup when a package imports you. So I can see under the hood here that it's allowing me to see that stuff, and I can see that there's basically no real things being initialized that are of interest. But in the main function, which is at the bottom part, we can see that we're just doing some weird slice part. And if you look in there and you look for a 3+2, you won't see it. Why? So the SSA stuff, it simplifies some of the expressions. So 3+2 is an integer and it's 5, right? So if you look in there in that function main, you won't see 3+2, but you'll see it's already simplified it to 5. And so certain things you wouldn't want to catch with this case. But this gives you a really cool, way of looking at the code to catch other types of problems that are of more interest. And this is a really cool tool, especially just for dumping, giving you another way to look at a piece of Go code, regardless. And using that, you would basically then try to do some sort of control flow or data analysis on the expressions as they're assigned and as they're called and passed around to the other functions in the program. And that allows you to do some really cool nested inspection that was definitely out of the scope for the talk tonight, but has really, really cool properties. And just want to basically give a thanks to all these people. All these people who either are working on the Go tools, or they've done blog posts, or whatever, like just done so much great work in the Go analysis sort of realm. So really cool stuff. Really appreciate their stuff, and that's really all. If you guys have any questions, I'll happy to take any questions. I also have stickers, HashiCorp stickers. So if you want something for your laptop, I got those too. But yeah, thank you so much. Really appreciate it.
Thank you very much to picat for that. That was amazing. And the rest of this time will be spent socializing, eating pizza. There's some beer in the fridge. Hopefully you enjoyed. And I will see you next time.